Take a moment to read this problem in detail. Pause if you need to. This demonstration is designed to show you basically how we take a series of distributions, the probabilities of which we've learned how to calculate, and combine them into chains of logic so that we can see how combined probabilities work over the long term. It'll also reinforce some basic ideas of the distributions as well as some basic rules of probabilities we go through. So it's a pretty comprehensive example. So let's just take it through it and see what's the probability when you're traveling that you'll be able to make all your connections and get to where you want to go without having missed one. So if you've traveled much, you've experienced some of this. Well, let's just go through and look at the problem in more detail. So the first variable that gets discussed is the number of connections you expect to take on your flight. And we were told it's a Poisson distribution with an expected value of 1. So to work out that distribution, we basically want to know our possible ends. It's a discrete distribution, so we know it starts at 0 and goes up. I've chosen to go out to 10 connections. That's more than I think we would have in a realistic travel example, but I'll take that as my distribution. I can then add the probability of each of those different values. So I'm using the Excel function for the Poisson distribution there. The Poisson probability of having 0 flights with the expected value of 1. And I've included false as the parameter because I'm not looking for a cumulative probability. I'm looking for the actual probability of that number occurring as I go through. So I can see that there's a 36% chance that I'll have no connections at all. So start keeping in mind as you look through this, what problem are we trying to solve? It's the probability of getting to our destination without having missed a flight. So if there's a 36% chance we won't have any connections at all, then there has to be at least a 36% chance we'll get to our destination without missing a connection. We wouldn't have any connections. There's a 37% chance we'll have only one connection, and then the probability falls very quickly after that. So I could have stopped at perhaps 7 or 8 connections because the probability of 9 or 10 is near 0. Whenever you do this distribution like this, always select all of the cells that you've done and look down here in the right to make sure that they sum to 1. If the values don't add up to 1, you don't have a complete distribution. So if this came out to like 0.998 or something like that, I'd have to add another row, perhaps with 11 connections and its probability. But I keep going until I know I've exhausted the probability. So the probability of being 0 to 10 connections is in fact 1. I don't need to go any further. Always check your distributions that you're building that way to make sure you haven't left off some important values. The next distribution we were given was the amount of layover time. So when you plan a trip, you not only plan how many layovers you're going to have, you have an option to book flights close together or far apart based on how much layover padding you're looking to allow as we go through. And the problem says that's, again, a Poisson distribution with an expected value of 2. But the actual Poisson variable is not of interest to us. What we're interested in is the allowed layover time, which is a function of the Poisson variable, 15 times x plus 1. So I can fill in the distribution for that. Again, I have my n. My n is my Poisson variable. Even though it's not the one that I'm interested in, it's the one I have to calculate my probabilities on. So I'm going to have that run from 0 to 10 as well. And then I've included the functional value of how many minutes of layover that would translate into if that happens. So when I plug in the probabilities, again, I'm using the Poisson distribution. The Poisson distribution, again, is against n, is against the Poisson variable. So the probability of having an expected layover padding of 0 and expected probability of 2, and again I'm using false, I'm not interested in the cumulative probability. So I'm calculating in column F the probability of the value in column D, but that's not the way I'll discuss it. I don't say there's a 13% chance of having 0 in my layover parameter, because nobody knows what my layover parameter is. What I say is it's a 13.5% probability of having a layover of only 15 minutes. Or there's a 27% probability of having a layover of 45 minutes. So that's how I do it. So the function that we learn in our distributions, that the Poisson distribution variable can be expanded to its function without altering its probability. Then I was given another variable for the minutes of lateness. When a flight is late, how late will it be? This isn't something that's necessarily in your control overall. You can perhaps pick an airport that is subject to fewer delays, so you can control it a little bit. But for the most part, once you're on the plane and it's late, it's going to be late by a certain number of minutes. For this one, we were told in the problem, this is an exponential distribution. Again, rounded to 10 minutes, it has a lambda of 0.45 and a value of 10 times x plus 1 on that rounded value. I'm cheating here. I want to use the rounded value, so I have a discrete variable in my spreadsheet, because if I don't, I have to go into integration on the function, and that's harder to do for laying out my joint distribution. So I'm converting, in this case, a continuous distribution that is exponential into the set of bar charts that would correspond to their 1 unit integrals over time. So again, I have my n from 1 to some arbitrary number, my function 10 times n plus 1, and to that I can add a probability. Only note, I've skipped the probability column j because this is a continuous probability. So the Excel function that gives me the exponential probability of 0 with a lambda of 0.45, and I use true because I'm interested in the cumulative probability. So the cumulative probability, say down here, of having a 0, 1, 2, or 3 is 0.741. So that's the cumulative probability getting to that point. So if I want to get the actual probability of just that number, I have to take the difference between the values. So this value is the current cumulative probability minus the prior cumulative probability. So in essence, what column J gives me is the integral over the unit space on the number line under the continuous exponential curve. I've done it in 1 minute intervals. I could have done it in 1 second intervals or 1/10,000 second intervals. In theory, I could make the discrete version of the exponential as uniform, as small as I want, and actually eventually get pretty close to the continuous distribution. So you have by increasing the parameter n, instead of doing 0, 1, 2, 3, I could have done 0, 0.1, 0.2, 0.3 on down. I ended up with a very, very long list and presumably a more accurate percentage. But be careful when you do that on an engineering problem. Look at the problem you're trying to solve. Think about a flight being late. When you talk about a flight being late, you don't really report. You say it's 10 minutes late, it's 20 minutes late, it's 30 minutes late. Nobody says it's 3.5 minutes late or it's 3.21 minutes late. Just because the exponential distribution is continuous doesn't mean you try to treat the problem you're trying to solve as completely continuous. So the fact is, 10-minute intervals on the lateness is probably good enough for the problem we're looking to solve. But if I wanted a smaller interval on that unit, I could simply change my n to be a smaller discrete value. Either way, I end up with a discrete value that I can use in my probability. So now I know the basic probability of a number of connections, the probability of how much layover padding I'm going to allow, and the probability for how late a flight is going to be. Now I'm ready to build my joint distribution. All I've done here is I've moved the data from up here to down here because I'm going to build my parameter, and it helps to have one of your distributions on the side because that will become, if you will, the rows of your distribution as you go. So all I've done is move the data at that point. But at that point, next to it to the right, and I've rolled down here to this level, I can build my joint probability matrix. That's what I'm basically building here. So typically the left-hand side of your probability matrix is one of your variables, and in this case I always do the one that I've brought down to that side, and the top, or the columns, is the values of the other distribution I'm looking to do, and I've copied that down with a simple pivot in Excel to turn what was a column of data into a row of data. Because I'm in Excel, I didn't have to bring this data here. Anywhere where I'm going to refer to this cell F2, I just as easily could have referred to cell B2 23, but I prefer to get the general layout as a conventional layout for how these matrices work, and I recommend you build them even if the data is somewhere else in the spreadsheet. I then bring in the actual marginal probabilities associated with that. So what I've got down here in the bottom is again pivoted, it's the probability column from the layover. So the probability of having a layover of 15 minutes was 13.5. Over here on the far right, I've got the probabilities associated with the lateness. So you'll see I've created a frame, if you will. So conventionally, the n, or the functional value, goes to the left and the top. The probability of those values goes to the bottom and the side. It's just a visual thing. You can build the cells to do anything you want, but this is the conventional way you tend to build it out as you go. And at that point, you're ready to populate the joint probability. So I've populated it here. The cells are all the same. So I typically only have to type this one column up, this one cell up here in G22. And it basically says take the probability in column R and multiply it by the probability in row 48 and use the $ to lock those in so it stays with column R in row 48. Then all you have to do is copy that cell and distribute it across the matrix. So you only have to type the formula once. You can just paste it in the rest of the values. And that gives you these values in the spreadsheet as you go. Okay, so now it's all filled in. We already validated that the probabilities on each distribution was 1. I'll I'll show you again. Here's the other one. So I already know that. So 1 times 1 should be 1. So one of the ways we test our matrix is we add up the sum of the probabilities we've just calculated. Make sure they add up to 1 also. If they don't, you did a typo someplace and something's wrong with your calculations, because 1 times 1 is 1 as you go through. So keep testing your spreadsheet as you're building it. In fact, for that one, we typically take and build the expected value up here on the top as the sum of all of those columns, because we want that value as we go through. Now, we don't actually want the value 1, we want a conditional probability, but to know you've built the matrix correctly, always fill in the expected values that you have it filled in. You know that it's 1, and then you're ready to make the change you want to do for the actual problem you're looking to do, and that is to get rid of some of the values. So what I've done here is I've modified the formula. If you take a look at the new formula, it's still R22 times G48, but in this case it's conditional. So it says if F22, okay, which is the amount of time of lateness, is greater than G21, which is the size of my layover. So if the flight is later than the layover I've allowed, then include the probability. But if the layover I've allowed is longer than the lateness, just include nothing in the cell, because I won't miss the connection. I'm going to make that connection. So I modify that cell, copy it across the whole table, and what you'll see is that the upper right of the table has disappeared. So this table is blank right here in K23, because if I've allowed a 75-minute layover and my flight is only 20 minutes late, I'm not going to miss my connection. Where down here, if I've only allowed a 75-minute layover but I'm 120 minutes late, I have missed my connection. So that's the conditional logic that the problem asks us to build in. And I do that after I've tested to make sure I get a 1 out of the whole thing, because that means I can trust this expected value that I get. There's a 34% chance, based on the parameters I was given, that the layover I plan won't be long enough to cover the lateness in what occurs going into my data. So that's an important number there in terms of the problem. And every joint probability is a little different, but it always comes down to modifying the formula in this table cell to include the constraint you're given in the problem. It could be anything. It could have been a reverse, that the layover is much longer than I want, or the layover, how often is the layover I plan an hour too long for the amount of lateness I encountered, to know if I'm wasting time. Whatever condition you can think of could have been built into the conditionality of this matrix. And that's the power of the joint distribution as I go through. So I now know that there's a 34% chance that I'm going to miss my connection if my flight is late. So the question is it late? The other parameter we were given in the problem is that the probability of a particular flight segment arriving late is a binomial distribution with a probability of 50%. So again, if you're thinking about your problem, we already knew back here that there's a 36% chance I won't miss a connection because I won't have a connection. There's a 36% chance I'll also have only one connection, and there's a 50% chance that flight won't be late. So half of that, 18% added to the 36, I'm now up above 50%. There's a better than 50% chance that I'm going to make all my connections just because of the simplicity of the data. But I want to put it together to see what the absolute probability is as I go through. So I want to take that probability and now use it to come up with some results. So now I'm looking at the results of the question itself. So I'm looking at the probability of being late and missing my flight. So that's the L and M. So the probability of being late and missing my flight is the product of the probability of being late, 50%, times the probability of missing my flight if it's late. That's the 34%. So like I said, 34% is the probability that my layover is not long enough, but it doesn't make any difference how long my layover is if my flight's not late. So there's only a 17% probability that my flight will be late and I will miss the connection because of it as I go through. So that's the combination of these two probabilities going through in series. But that's for one connection, but sometimes I'm going to have more than one connection according to the data. So to keep going, I have to look at the probability of making my flight. So 1 minus p is the probability that I won't miss my connection, won't be late and won't miss a flight. So if I have 0 connections, the probability of not being late is 1. The probability, if I only have one connection, the probability is 82%. So that's 1 minus that 17% value. But the probability of getting through 2 connections without missing is only 68%, and that's because when I subtract p from 1, I have to raise it to an exponent, which is the number of connections. So the more connections I've got, the lower probability that I'm going to get through all the flights. So down here, if I've got 82% chance, 83% chance of not missing a connection in each flight, but I've got 10 flights. By the time I raise that number to the 10th power, the probability of getting through 10 flights without missing a connection gets really, really low, even though there's only a 17% chance of a flight being late and missed. It gets pretty bad as I go. So I can now take those numbers and subtract that from 1 to get the probability for that number of connections of actually missing my flight as I go through. So the failure is 1 minus this success number as I go through. And then lastly, I just have to weight that probability to get my final answer. So the expected failures under this column is not just the sum of column L, but it's the sum of column L weighted by the probabilities over in column B. So multiply the failure rate by the probability of having that many flights. So while the probability of failing is very high for 10 flights, the probability of having 10 flights is very, very low. So it doesn't add much to the total. So it turns out there's a 15% chance that I will miss a connection cumulatively across the entire model. 1 minus that number is 84%. There's an 84% chance I will get to my destination without having missed a flight. Now, 84% chance is also the sum of the success numbers multiplied by the probability. So I could have calculated it that way. I just chose not to. You can get to the same numbers in multiple ways. So going back to the core problem, if I accept the parameters I was given in the problem, there's an 84.3% probability that I will get to my destination without having missed a connection.